Today I'm going to talk about different kinds of robustness in statistical learning problems, the bad decisions we can make, and how we might try to make them a little bit more valid. So my motivation is that basically I don't want, it's sort of similar to some of the things that Dorsa is doing. I don't want machine learned systems to fail when they get into the real world. And often they do weird things, right? So let me motivate this by a couple of examples. So the first one is that I read this in Wired a couple of weeks ago. Liking curly fries on Facebook reveals your high IQ. I think there's some nods in the audience, maybe. I don't know. Maybe you guys have experience with this. But to me, this suggests, well, a failure of reporting. But also, this just seems unlikely to be robust to small changes in the underlying data, right? Like, it sort of seems fairly clear that curly fries and intelligence should be more or less independent. Another challenge, if we're building self-driving autonomous systems, things like this, we're going to give them a bunch of training data. Say they learn to drive in California, the weather's nice, you can drive a convertible, and then right there I have a picture of driving in Fargo, North Dakota in the winter. So you can see the environments are a little bit different. Challenge 3 is oftentimes, especially in these big sort of deep learning models, there are what are known as adversarial examples, where you can take an image, say on the right, which looks exactly like a panda, and your model may be very confident that it's a panda. You can add some tiny, tiny amount of noise to it, which is imperceptible or more or less imperceptible to your eyes or my eyes. And you can make your predictor, say, extraordinarily confident that you're seeing a gibbon or something else. All right? And to paraphrase Dan Benet, we could put a transparent film on a stop sign that's basically imperceptible to a human, and the computer would see the stop sign as air. So these things sort of seem like problems, right? And this is one of the directions that my group is trying to tackle, make progress understanding. So let me, with that as motivation, let me now just jump in and talk about sort of what we're going to do. And I take a fairly mathematical approach to things, but we try to actually have impact on a lot of the real-world problems we run into. So the setting that I'm going to work in is what's known as stochastic optimization. So here, I get a bunch of data, which we represent as, say, a sample x1 through xn. This could be scenarios in driving or different images. And I have some parameters, or a predictor or a controller, theta, that I want to learn. And I suffer a loss, L, on a data item x with parameters theta. And what I really would like to do is solve some kind of population problem where I want to minimize my expected future losses, from whatever distribution is generating my data. And the challenge is that typically the distribution generating the data isn't really known, right? I don't know where my data is actually coming from. I get some samples, or I go around and drive and get some examples from driving, but I don't exactly know it. So the question is, what do we do? So the sort of classic statistical choice was what's known as just empirical risk minimization, or you just take your data, average your performance across the data you've actually observed, and try to make that as good as possible, which is what we're showing on the bottom here. But this basically runs into all the problems that I originally described. So let me give a few pictures. So let's suppose I take a sample from a world where there are just 4 different scenarios out there. There's a scenario A, scenario B, scenario C, and scenario D. And I'm going to count how many times in my sample I see A, B, C, or D. So here's one sample. Here's another one. Here's another one. Here's another one. All right, you can see that all of these, these are all samples from the same distribution, but they have quite different counts of how many times each scenario actually showed up. Right? So even in just 4 samples, I'm getting a gap of, say, in my 4th sample, or in my 3rd sample, the 4th scenario showed up, say, 3 times, and in the last one it showed up 9. Okay, so there's a huge amount of variability in these things that we want to actually try to understand how to deal with this. These things just change all over the place. So how do we deal with this variability? And our approach in my group is what's known as, we're building on some tools known as distributionally robust optimization. And so typically what we do is we say, okay, let's just average our losses across the scenarios or data we've observed. But what we can do is say, hey, instead of averaging our losses, let's try to be a little more adversarial. And let's come up with algorithms that say we're going to guarantee that as long as the data is somehow in a neighborhood of the data you've observed, then we're going to do well. So instead of averaging our loss, we sort of maximize our average, or we maximize our losses in some, say, neighborhood of the distribution. And so the idea is we're going to try to do well almost all of the time instead of just on average. And more generally, we can solve what's known as distributionally robust optimization, where we say, hey, I'm going to just give you some set script P of distributions. You don't know what it is. You'll get data from one of them. Try to minimize the worst possible performance across all of these distributions near where you're collecting data. All right, so don't just do well on the data you're getting, but do well on all sort of possible data sets nearby. Okay, and what we can do is by sort of statistically principled choices of these distributions, we can actually derive optimality certificates. We can say, hey, as long as you minimize sort of the worst case error across this family of distributions, I can certify you're going to have good performance going into the future. So here's this is just kind of a picture showing what's going on. It's a little bit funny to look at, but suppose that there are 3 different scenarios in the world, x1, x2, and x3. Typically, you just say, okay, I get one sample of each. My empirical distribution is just that dot in the middle. I guess you can't really see my laser pointer. Maybe you can see the mouse. So I got this dot in the middle. So this is where we typically would say, hey, our data are all right here. Let's do well on that dot. But what we're going to say is, hey, there's a number of sort of possible distributions in these increasing circles going out toward the edges of this set of distributions. We want to do well across all distributions that might fall in one of these. And so we're going to try to penalize things by looking at all distributions nearby our distribution. So basically what this ends up doing is we say, okay, you're going to get some examples. The typical approach just says treat each example as the same. Doesn't matter if it's a hard example or is an easy example, just do equally well on all of them. And what we do is we say, hey, on hard examples, those for which you suffer a large loss, in this case the losses are the black line, so that's this line going down right here. On these hard examples, let's upweight your penalty. So this is this red line. We've upweighted from, say, average of 0.01 to 0.06. And on the easy examples, you just kind of ignore them. If you're doing well on them, you're going to ignore them. So we're going to basically, in careful ways, try to reweight our data set so as to focus more on the difficult elements. When we do this right, what we can actually get is our certificates. So let me just give a bit of an aside. So we try to solve, in optimization, what you often try to solve are convex optimization problems. So why do you solve convex optimization problems? Well, because they're computationally efficient, and we know how to solve them, and when you solve them, you can certify that you've solved them. And what we want to do is give sort of similar certificates for these stochastic problems. We want to be able to say, hey, you've solved this problem. I can certify that you're going to get good future performance, right? We want to basically do verification or falsify that you won't have good future performance. Okay, and the nice thing here is that with these distributionally robust optimization problems, we actually do get convex optimization problems, and we can actually develop efficient solution methods for solving them, which are just as good as, say, your favorite stochastic optimization methods that we often use in large-scale statistical or machine learning problems. So basically, so just as a quick description of how we develop these algorithms, basically we've developed a family of algorithms that essentially treat learning as kind of a two-player game. And one of the players is an adversary who's trying to feed you the most difficult examples, and the other player is the learner who's trying to do as well as possible. And by developing basically some carefully designed tree-based data structures for our adversary, we can basically have this game which goes back and forth between the adversary and the learner, where the adversary can efficiently generate difficult examples, and then the learner runs a stochastic optimization scheme which is just as efficient as sort of standard learning methods. And we go back and forth between these in effort to actually do our learning. Okay, so let me now describe a little bit about the guarantees that we can give for these problems and how we might actually certify good performance. So as I said before, the standard approach is to just minimize your average loss on the data you've observed. Say you got a bunch of data, you try to do well about equally on all of it. And we sort of hope that this is approximately as good as actually doing well on your population. You know, you want to have a low risk or a low error on your population. But this isn't always the case, and we'd like to be able to understand when it's not. So that's what we're going to develop now. So basically, in any learning system, or in any statistical modeling system, or any machine learning system, you've got this what's known as the trade-off between bias and variance, which says that, you know, whatever model you've learned, or whatever controller you're building, or predictor you're building, you have some bias, meaning how well it can actually do on your data. And then you have variance, which is, you know, as the data changes, how much do your predictions change? And intuitively, if your predictions change hugely as your data changes a little bit, then you maybe don't expect to generalize as well. And if your variance is very small, then you might hope that, well, if my predictions always have small variance, they don't vary a lot, then that's a good thing, and I'm going to be able to certify that I can generalize better. And so what you might like to do is say, let's choose controllers, predictors, let's learn models that actually try to minimize the trade-off between these two objectives. You know, we want to do well in terms of bias, we want to minimize some measure of the variance of our predictions. Because if our predictions vary a lot from domain to domain, then we're not going to generalize well. This is a great idea. If we could do this, this would be awesome. Unfortunately, this is hard. And I can draw a picture of the type of objectives that you get when you try to do this. They look something like this. So if you're familiar with convex optimization, or just optimization in general, you know that when you minimize things, you want them to look like bowls, because then you go to the bottom of the bowl and you're in good shape. You don't want local minima, you don't want them to be not smooth, you don't want them to have kinks, you want them to be nice, smooth, bowl-shaped things. This is not shaped like a bowl, right? You've got kinks, it's got a local maximum here, you've got strange local minima, so it's actually very challenging to do this. So we can't do what we wanted to do originally, which is directly just penalize for the variability of the predictions you're making. But the neat thing is that, and this is some work that I've done with one of my students, Hong Namgun, these distributionally robust optimization schemes actually allow us to directly approximate this sort of bias-variance trade-off. And so by trying to do this sort of worst-case game where an adversary chooses difficult data, the learner tries to do well on these difficult samples, you can actually learn to trade off directly between this bias and variance. And you can actually prove a theorem that says this is what you're doing. All right. And then we can prove a number of theorems that actually say these really are, you really can certify that your behavior, if you run this sort of two-player game where the adversary chooses hard examples, you try to do well on them, you can actually prove that you get this optimal trade-off between the population risk, so that's R of theta, and the variance of your predictions. So your variability of your predictions gets smaller. All right, and anyway, so this to us is quite exciting because it means that now we really can, we really are seeing sort of this automatic way of trading off between difficult data and doing well on average and trying to control the variability of the predictions we've made. All right. Anyway, so let me talk about a couple of different experiments we've done here, just so you can see sort of what the effect of running these things is. And these will be fairly small scale, and we're working on making them larger scale and applying them in a lot more general scenarios. But so remember what I said is that these procedures, what we try to do is we try to upweight difficult examples with these games, and we try to do well on these difficult ones. So intuitively, what should we expect if we actually ran this on some real data? Somehow we might expect that rare examples or uncommon things are going to be challenging, and we might expect that if we try to do these distributionally robust approaches, we should do better on our rarer examples or our rarer scenarios. So here I'm going to just give an example of trying to predict the subject of different text documents. So I'm getting documents from the Reuters news corpus. Each one is about some combination of corporate, economics, government, or markets. And we have, it's a 50,000 dimensional problem. We have 800,000 training examples. And I'm going to talk to you about what's known as precision and recall. So precision is how many times are we correct out of the times that we actually guessed that something was an example of corporate or economics or a government or a markets article. And recall is how many times we were correct of the actual number of true correct ones. And I'm not going to delve too much into this, but what I'm showing here is sort of I'm plotting here the recall versus how much robustness we're trying to certify for a common category. So the articles about corporations are very common in our data set. And you can see that as we increase our robustness parameter, things don't change that much. I mean, we go from 90% accuracy to about 92% accuracy. So that's no big deal. But the interesting thing is actually in terms of sort of the rare categories. So economics is relatively rare in this data set. And by upweighting these economics examples, which are essentially difficult because we don't see them as much, we go from accuracy about 68% in their predictions, which is sort of the standard machine learning approach, to 80% as we increase this sort of variability penalty or these robustness penalties. And essentially what we're trying to do, and this is what you would really want in, say, a system you're releasing to the world, is you want to do well almost all the time instead of just on average. You want to make sure that it's not average performance I care about. Perhaps it's just like, let's make sure I always do well rather than on average. And what you see here is we're actually getting that. So basically we take, on frequent categories, we're going to not change our performance too much. But on infrequent things like economics, we're drastically improving our performance. All right, so in the last couple minutes, I just have about 5 minutes left in this talk. I want to give a quick vignette on a different type of robustness that we've started exploring and we've started to see some real successes with. And so I started by motivating this talk by saying we don't want machine learned systems to fail when they get in the real world. And I think perhaps even more saliently, it's a little bit irresponsible for us to release systems into the world whose robustness we don't understand. Right? I mean, we've seen in recent examples in the news of major failures because perhaps we didn't understand what some of the failure modes of our systems were. And our challenges, of course, are this image challenge where we add imperceptible noise and it changes pandas into gibbons. We try to learn to drive in California and then we go to Fargo. Remember, Fargo is the leftmost picture on the bottom. So there's all these challenges. And so what we might really like to do is actually, what we're going to try to really do now is learn to actually just change our environment completely so that we can look at more difficult environments. It's not just reweighting difficult examples now. Let's actually change the environment where we're learning the data. Let's try to develop schemes that can actually do that. And the way to do this is what's known as some tools from robust optimization. So what we do is instead of, say, upweighting data or reweighting data, we're actually going to modify our data directly to make it more challenging for our learning systems. So if you look at this, what I'm doing is I'm saying, we have data Z, and I'm going to add perturbations to it to make it more difficult for my, learner. And there's been a lot of work on this in the machine learning literature recently. These ideas originally were developed in, say, the design of bridges and things like this in the 1990s. But there's this minor issue that usually trying to actually solve these things is at least NP hard. And so we just do a bunch of heuristics, and they may or may not work, but we're never really satisfied that we can actually get good behavior. And so the question is, how do we figure out how to change the underlying data the right way to actually guarantee future good performance, or good performance sort of everywhere? And the approach that we take is what's known as Wasserstein robustness. What it is perhaps not super important, but the intuition is that we've got our data, which say the original data is this kind of orangish, yellowish bucket, and we're going to try to move. We're going to try to move as much of it as possible to some more difficult region, say this blue region where things are more challenging. And so we want to say, okay, I want to look at all distributions where they are close in this Wasserstein metric, or basically what's known as an Earth mover's distance. How efficiently can I move data from over here to over here? And it turns out that with a couple of a priori this is still NP hard, which, okay, whoops. So we're still kind of stuck. But what we've done is actually developed a way of using duality, convex optimization duality, to actually be able to solve these types of problems. And so mathematically I can write down what we're going to do. What we actually do is we just sort of penalize the changes in the underlying data that we're going to make, and we say, hey, let's look at worst case changes with this penalty for changing the data. It turns out that this is actually something you can computationally feasibly do. And by some careful convex duality arguments and a few different, a few different proofs that we've worked out, you can actually imply that this approximates the problem you really want to solve, which is how do you change the underlying, actually change the environment that you're working in. Okay, so we can develop algorithms for this, but since I'm running out of time, let me just show you a few different ways of reading the tea leaves. So we can actually develop efficient schemes, but what I'm showing here is now we're actually going out and applying this to digit recognition systems on fairly large-scale, non-convex deep learning models. And so what I'm plotting at the bottom is sort of a notion of how robust we are to changes in the underlying images. And on the vertical axis is our error in terms of predictions. And there are a number of different methods. The black one is sort of just classical machine learning, minimize your average error. So very quickly, it's doing very poorly. Your error is nearly, well, 1, which means you're essentially making random predictions. But you can see this red line with the box here, this is us. We're getting a substantially better performance than essentially every other approach to these things. And because I think this image is kind of nice and evocative, it's a little bit reading tea leaves, so this is not anything formal. But what I'm showing here is an image, which is an 8. And then we have 5 different learning methods that different folks have proposed for actually making predictions. And I'm showing how much we have to perturb the 8 to get the learning method to classify it as a 3. Okay? So the middle image here, right here, on the top, is the classical machine learning, minimize your average error. So that perturbation, I mean, you and I look at that, and it looks like an 8. But the machine learning system thinks this is a 3, so it's very confused. Then there are some different heuristics that folks have used. So one is known as the fast gradient method. This is the perturbation that confuses it. You can see this more or less still looks like an 8. There's an iterated fast gradient method, still looks like an 8. There's a method which uses projected gradients, and you're starting to see that these perturbations actually kind of do start to get things confused with this sort of these methods based on actually changing the underlying data. You know, moving the data set from one place to another, changing the actual environment. You can see this is the bottom right image. To get this thing to classify an image as a 3, you actually have to make it look like a 3, right? I mean, you and I think, look at the bottom right image, and we might think, yeah, that's actually a 3. You know, so this is a little bit reading tea leaves, but we see this kind of behavior a lot. And you can actually get substantially better generalization performance via these robustness ideas. So let me just conclude here. What we're trying to develop are procedures that leverage convex optimization so that we can actually solve them, certifiably solve them, give certificates that sort of trade off optimally between some notion of robustness or variability in our predictions and performance. And empirically, we often get a lot better performance on difficult instances. So here are 3 references, 2 from the last NIPS with my student Hong Namgung, and 1 that will be appearing in a month or so at the International Conference on Learning Representations with Aman Sinha, Hong Namgung, and me. So thanks for your attention. I'm happy to take a few questions. Yeah.
I have 2 questions. The first one is the pictures that you show with the numbers, handwritten numbers. Some of them look very much like the experiments people do to poison data, right?
To what data, sorry?
To poison data.
Yes.
Those papers. So I'm wondering if you are feeding your system numbers like the one that looks like a tree. Are you maybe going to end up with a model that is poisoned by your defense itself?
Yeah, so the question is basically, you know, okay, so, you know, by being robust, are we going to have worse performance because we are robust? And there is always going to be some kind of trade-off between robustness and performance, and trying to nail that down is very important, yes. So, I mean, you can, well, I guess I don't have a plot there. So yeah, there is some kind of penalty. Empirically, we see that these penalties aren't so bad, but this is something that we don't completely understand yet. I mean, it's not quite data poisoning, but it does impact sort of performance on easy examples just because we're trying to be more robust. It's on now. You're good.
Okay. My second question was about when you had that class that was not represented well. I think it was economics articles, right?
Yeah.
I'm not sure I understand why you're able to get better performance when you're not seeing a lot of data there. And I was wondering whether you can comment on why you are getting those results, and also how are you modifying the decision boundary there so that it doesn't go against like the overall objective, because at the end of the day, you don't have enough data to know whether you're moving one way or the other, right?
Sure. Yeah, so that's a great question. And the answer is, one answer is that if you think about sort of a variance penalty, then, if you dig into sort of what the variance of a loss actually looks like, or the variance of a prediction actually looks like, an infrequent class, or rare examples, will have a disproportionate effect on the variance of your predictions. And they won't change kind of the average error very much, but the variant, if you do poorly on a rare class, the variance will be sort of disproportionately blown up. And so by decreasing that variance, you can actually guarantee that, as long as, basically just by decreasing that variance, you're guaranteeing that you do better on those classes. And then in terms of how do you make sure you don't do worse on something else, well, that's where the original sort of basic bias term comes in. The frequent classes, you do well because of that. The infrequent ones, because of the relative penalties on variance. Yeah. Is there something over here?
We're actually out of time.
Okay. All right, we're out of time.
Thank you, John.
Thank you.